So we are protecting websites and mobile applications all around the world, here in the US, in Europe, and in Asia. And that's how we can collect a huge amount of data to train our AI and to run the bot detection part. We are focused on the OWASP category around automated threats. So the OWASP is classifying those threats like account takeover, credential stuffing, denial of services, and scalping. And of course, as all of us, we've seen a huge increase in threats like credential stuffing lately. So the agenda today will be around the bad bot. How sophisticated are they today in 2021? Then Antoine will talk about the detection techniques. And finally, we will have a zoom on one of the machine learning algorithms that we are using at Datadom to detect the most sophisticated bots that have never been seen before. So what does a bad bot look like in 2021? So we are facing many different challenges. First, the bots are targeting every single endpoint. So let's take an example of a standard application today. So we have servers and APIs available publicly. And then we have the consumer on the client side, like a mobile application, a web application, or an HTML website. So that's what we are calling the client side. What we are seeing is obviously that the bad guys are trying to reach the servers and the APIs, and that's something that must be protected. But by the time we've seen that the bad guys are also trying to reach the mobile application, the web application, and the HTML website, that must be protected. In general, the hackers will try to find the weakest spot on any website or application where they could get access to the data. The second big challenge is that bots are using the same technologies as humans. So they are using a real browser, for instance, like Puppeteer or Chromeless to get access to websites and to evade the basic detection. The hackers are not using curl anymore because this is too obvious to be detected. And on the mobile part, they are using real mobile device. I don't know if you have seen this video, but today you can run thousands of real mobile devices that can execute real native application to generate fake views, fake click, fake reviews, or scrap the content. The first biggest challenge is that the attacks now are heavily distributed. It's not like a few years ago where the cat and mouse game was around just blocking the most important IP addresses in your IP table list. This is an example of a recent attack that we've seen on one of our customers' websites. The attack was coming from millions of different IP addresses. And each of those IP addresses, they were just doing one or two login attempts. So that means any approach that is trying to catch the bad bot just being IP-centric cannot catch those kind of attacks. Also, the bots now are using super clean IP addresses. So, of course, they are still using data centers IP addresses. So you can see a huge amount of traffic coming from AWS, Azure, GCP, or some cheaper cloud provider. Of course, we still see some IP addresses coming from organization, but the rise of the residential IP addresses involved in bot attacks is just insane. Today, it's 30%, but this number is growing and doubling every year. Why? Because it's now available super easily. So you can just pay a few hundreds of dollars to get access, for instance, here in the US, to IP addresses coming from Comcast, AT&T, or Cox, or mobile ISPs like Sprint, Verizon, or T-Mobile. That's globally infected mobile device that will be using those IP addresses and that you can use as a proxy using just a few command lines. And also now bots, they are able to pass CAPTCHA. So you know that during the last few years, websites and mobile applications tend to use CAPTCHA to be protected against the bot. But with two different techniques, they can evade those kind of protection. We can see that they can pass the CAPTCHA using Chromeless, Puppeteer, for instance. and using AI and machine learning to run image recognition. And on the other side, they can use solution like TrueCAPTCHA, where human will be involved. Sometimes it's even cheaper to involve human rather than using a lot of CPU to compute some AI. And finally, and that's probably the most sad part of the story, is that it's not only available for the most advanced engineers and hackers. You don't need to be part of a huge hacker group because today this is available through some solution as a service. You can, on one side, get access to the best advanced browser as a service solution, like browserless, for instance, and use it in combination of a mobile residential IP addresses proxy as a service, like Illuminati. And without any specific knowledge, you can just start creating a very advanced bot, actually. And that's, for instance, the move that Illuminati did by moving from just a residential proxy IP addresses to add the scraping part and the browser part. So now anyone, any newbie can just run a massive attack using just a few dollars and one of those solutions. So now, Antoine, the floor is yours.
Thank you, Benjamin. Can you hear me?
Yeah.
Okay, so now I'm going to talk about the bot detection techniques that we use to catch these bad bots, and later I will finish by describing one of the machine learning approach that we use to detect credential stuffing attacks. So when it comes to having the best bot detection, it requires to collect as many signals as possible and being able to process them in real time. That's why Datadome collects billions of signals a day, ranging from browser fingerprinting attributes, collecting with our JavaScript tag, running on hundreds of millions of browsers every day, to mobile fingerprints that we collect with the help of our SDK on millions of devices. In addition to the signals, we also collect information like the user behavior. And so what do we do with these signals? So first, when we receive an HTTP request, we will enrich it by adding new signals such as the country around the IP address, like the country, the autonomous system, whether or not the session or the IP has recently conducted malicious activity. Then, in parallel, we will execute in less than 2 milliseconds a set of different approaches that are all necessary to obtain the best bot detection as possible. So first, we will verify if the request is coming from a verified bot or a good bot like Google Bots, and whether or not it matches custom rules created by our customers in their dashboard. We'll verify if it matches a set of non-signature of bots, for example, bots with a discriminating ATS fingerprint or bots that have non-client-side fingerprints. And then we will apply a set of machine learning detection techniques. I will provide more details on this topic after. So regarding verified bots, regarding verified bot, it's often an underestimated task in bot detection because we think it's easy to authenticate good bots, but it's common for attackers to lie about their identity to try to fool a defender. So for example, according to our own statistics, around 30% of all bots claiming to be Google bots are not Google bots. To conceal their true nature, bad bots hijack the official Google bot user agent and use IP addresses from Google Cloud Platform to pretend to be a legitimate Google bot. And if you want to apply Google's own authentication recommendations, it can be cumbersome to apply in real time. That's why at Datadome, we have an in-memory database of this kind of bot patterns to reliably and safely authenticate good bots and verified bots. Also, constant vigilance is still required as hackers keep coming up with new ways to disguise their bots as being good bots. For example, recently, the threat research team discovered that Facebook links preview feature was being used as a proxy by web scraping bots. Because Facebook bots are typically authorized or whitelisted by website administrators, the preview API opened a backdoor for bad bot operators. So we contacted Facebook and they now applied rate limiting to fix this issue. Now, there is another set of bots that we can identify based on their signature. So the least sophisticated bad bots are relatively easy to detect by looking at known bot signatures. These are specific patterns in the incoming HTTP requests, which we know belong to bots. So bot signatures can be extracted from different categories of signals, such as HTTP requests and headers, TLS fingerprints, browser fingerprints, so fingerprint collected with JavaScript attributes, and mobile fingerprint collected with the use of a SDK. So for example, when we receive a request, we look for inconsistent HTTP headers. If a visitor pretends to be a legitimate Chrome browser, but doesn't send the appropriate headers that should be present with this Chrome version, or sends header with values that are not consistent, then it will be flagged as suspicious because it has an invalid signature. And now I'm going to explain how we use machine learning approaches for bot detection. So Datadome detection engine leverage a wide range of machine learning approaches to detect malicious traffic. The philosophy of machine learning at Datadome is to use a wide range of machine learning models, each one responsible for a particular task. For example, we leverage supervised learning to analyze consistency of fingerprints and determine the reputation of an IP address. We leverage unsupervised learning to apply outlier detection on website traffic and detect when there is an anomaly. And we also use semi-supervised learning to detect CAPTCHA farms, for example. The outputs of all these models is combined using a technique called model stacking, and then it enables us to take a final decision, so whether or not we allow or block the traffic. Now, I'm going to present a use case of applying machine learning to bot detection. So that's an approach that we call AI login response, which is specialized in detecting heavily distributed credential stuffing attacks. So attacks conducted on the login endpoints where each IP makes few requests. So it's a combination of outlier detection and malicious traffic isolation specialized for credential stuffing. But first, how can we apply machine learning for bot detection? Machine learning for bot detection can be applied at different granularities. We can apply it on each HTTP request to classify, for example, whether or not the signature is legitimate or not. We can apply it on IP address or on session to observe whether or not the behavior of this session or of this IP is legitimate or if it can be linked to bot activity. And we can also observe the whole traffic of a website or of a mobile app to determine if globally the traffic is legitimate or if a significant part of the nature of the traffic changed and is linked to malicious activity. The approach that we will present today operates on two granularities to optimize the detection. First, we monitor all the website traffic. So all the website traffic is monitored using different techniques that I will present after. And then we operate also on the HTTP request. The idea is to be efficient against heavily distributed attacks because they cannot be detected by looking only at each request. We need to monitor the whole website traffic. And also to be efficient against bots that constantly modify their fingerprints in order to avoid detection. So this solution is in 3 steps. First, we identify the blocking patterns that the blocking patterns need an update. So it means that we need to detect that there is an attack going on. Then we will infer the set of malicious fingerprints among all the website traffic and generate blocking patterns to block only these malicious parts. And finally, we will enforce these blocking patterns in real time so that all the requests part of the attack are blocked. So first, let's look at how we detect ongoing attacks in real time. So for every customer, we monitor a set of aggregate statistics on the login endpoint. For example, on the login, we will monitor the distinct number of user agents, the distinct number of IP addresses, of countries making requests on this endpoint. And we will apply outlier detection on this time series. So as you can see on the picture, it's only with 4 time series, but these are signals that we monitor. And for each of them, we apply an outlier detection algorithm in real time in a streaming detection engine that will detect when an anomaly starts to happen. And if we detect an anomaly, then we will push an event describing the attack. So we will send an event saying that for a given customer at a given time, a given attribute starting varying abnormally. So now that we know that an attack is going on, we need to identify the subset of malicious traffic among all the website or application traffic. And how do we do that? So for this particular machine learning approach, we focus on server-side fingerprints. So by server-side fingerprints, we mean attributes that can be accessed when we retrieve a request, such as an IP address, along with all the information that can be enriched with an IP address, such as the autonomous system, the country, whether or not it's a proxy. We will also use information from the HTTP headers, the TLS fingerprint, as well as URL visited. And we can use basically any attribute available on the server side. We will call it a fingerprint. And then the goal is to analyze each request. So for each request, we will extract a given fingerprint. So from a mathematical point of view, a fingerprint can be seen as a set of categorical variables, AI, that have a possible set of values. And we'll try to generate blocking patterns. So what we call a blocking pattern is simply a conjunction of attribute value pairs. So to give you an example, it could be something like user agent is Chrome 92 and TLS fingerprint equal 133 in 93 and other attributes. So we can add as many clauses as we want to generate the patterns linked to malicious activity. How do we do it? So to give you an intuition behind our approach, the idea is to find discriminating attributes to identify what changed between before and after the attack started. So the graph that you see on the screen shows the evolution of different attributes and values, such as the list of headers, the autonomous systems that are targeting the login endpoint of a customer. And for all of them, we see a spike for certain values, which are linked probably to the fingerprint of the attacker. The goal of our approach is to do it, but not only in 2 dimensions, but it's to mine discriminating blocking patterns linked to the attacker. So how do we do it? So we started by using a modified version of an algorithm called Stuco, which is a contrast set mining algorithm. And we adapted it to address the real-time requirements that we have at Datadog, because we need to react as fast as possible to detect and stop attacks on the login endpoint. The goal of the algorithm that finds the contrast set is to find contrast set. So it's to find what differs between before and after the attack started. And so to do it, we apply the contrast set algorithm on 2 groups of data before the attack, during the attack. Our approach generates contrast set, which in our case, we call blocking patterns, since they characterize the potentially malicious traffic of the attacker. Once we have identified a set of potential candidate blocking patterns, we define evaluation metric to choose the best ones. By best ones, we mean the ones that block the most malicious traffic, all while allowing human traffic. And if it satisfies our acceptance criteria, we enforce these blocking patterns in real time. So one thing that I feel is important to say is that our blocking pattern, this approach is really safe against legitimate spikes of traffic, because all e-commerce websites, all news websites will have spikes of human traffic. Maybe because they buy advertising, or they organize flash sales, or there is Black Friday, or maybe it will be unplanned. There will be breaking news. So our approach is resilient against this kind of situations. Indeed, the goal is to detect a distribution. Yeah. We don't see. Okay, I will continue. But our approach aims to detect a shift in distribution between before and after the attack. In case of a legitimate event, then we will see the same distribution, but with a different scaling factors. So our approach will be resilient. Moreover, in a previous slide, I talked about acceptance criteria and evaluation metrics. It means that we don't accept all the blocking patterns. We evaluate them against some metrics, and also we evaluate how they would have performed in the past to ensure that it wouldn't block any human traffic. And once we have identified this set of legitimate blocking patterns, we enforce them in real time. And as we see on the screen, so it's the result of this algorithm applied on a credential stuffing attack on a customer mobile login endpoint. So the vertical gray line represents when the attack was detected by our outlier detection model. Then our contrast set mining algorithm starting to generate and find malicious blocking patterns. And so in red, the red line represents the traffic that has been blocked by the blocking pattern generated by AI login response. In green, the good news is that in green, which is the allowed traffic, we see that the allowed traffic remains stable over time, which is a good sign because it means that human activity remains stable. It means that it was not impacted by our blocking patterns. And so that our blocking patterns were responsible only for blocking the malicious part of the attack and not the legitimate part of the traffic. Thanks to this approach, we were capable to quickly detect an abnormal change at the whole website scale and generate several blocking patterns to block the malicious part of the traffic.
Yeah, thank you. So to wrap up, the key takeaway around the automated traffic and the different threats is that today the bots and the human are using the same technologies and IP addresses, that the event tracking and the behavioral detection is key in this fight against the automated traffic, that the bot protection must be done in real time using automated process because attacks are going super fast, and that we have to leverage all the different machine learning solutions using supervised, unsupervised, and semi-supervised to be able to detect evenly distributed attacks and that can change in terms of shape in real time. So thank you for your attention. For any questions, we have the Q&A coming, and I guess we will have the Slack also open to discussion.